I'm very glad to introduce our work OneTracker, Unifying Visual Object Tracking with Foundation Models and Efficient Tuning, which is accepted as highlight by CVPR 2024. Visual object tracking aims to localize the target object of each frame based on its initial appearance in the first frame. In addition to the conventional RGB tracking, there are various downstream tracking tasks that incorporate additional information and boost performance, including RGB plus N, RGB plus M, and RGB plus D/T/E tracking. In RGB plus N tracking, the natural linguistic descriptions of target are additionally provided to exclude the interference of similar objects and enhance the localization. In RGB plus M tracking, the masks of the target in the first frame are offered instead of bounding boxes. In RGB plus D/T/E tracking, the depth, thermal, and event maps are utilized as an extra to handle with the vulnerability of RGB trackers to complex scenarios and improve the robustness. The goal of all these downstream tasks is to localize the target with the assistance of multimodal information. Thus, we unify them as a whole, terming them as RGB plus X tracking. Despite the diversity of tracking tasks, the core objective remains the same: temporal matching or localizing the target in the search frame given its initial appearance, which is similar to the underlying principles of human attention mechanisms. Thus, based on this common ground, we present a general framework to unify various tracking tasks under a single framework by leveraging the power of foundation models and efficient tuning techniques, termed as OneTracker. Inspired by the advancement in NLP, our OneTracker consists of foundation model training and parameter-efficient tuning on downstream tasks. OneTracker firstly presents a foundation tracker for RGB tracking tasks, and then adapts it to RGB plus X with parameter-efficient strategy. In detail, we pre-train a foundation tracker on several RGB tracking datasets. After the large-scale pre-training, foundation tracker possesses strong localization capabilities, allowing it to accurately locate the target object in the search frame based on its appearance in the template frame. Then, we proceed to fine-tune foundation tracker on specific downstream RGB plus X tracking tasks, referred as prompt tracker. Different from previous RGB plus X works, which add an additional module to fuse multimodal features, we regard the multimodal information as a kind of prompt and provide foundation tracker with complementarity in a prompt tuning manner, termed as prompt tracker. With the general definition of RGB plus X tracking, the prompt tracker leverages a unified prompt embedding module to transform different modality downstream information into a cohesive token representation. After unified prompt embedding, we propose the cross-modality tracking prompters, CMT prompters, to fuse the extra information. In contrast to leveraging an extra parallel module to fuse multimodal information, the CMT prompters introduce multimodal features in a prompt tuning manner. CMT prompters learn semantic understanding of multimodal information and integrate it with RGB images. CMT prompters consist of multiple linear layers and a prompt fusion module. Firstly, the matching results and prompt are mapped to lower dimensional latent space using a linear layer, respectively. Subsequently, a prompt fusion module is employed to integrate the modalities. For RGB plus N tracking, cross-attention is utilized to merge the linguistic feature and temporal correlation. For other RGB plus X tracking, matching results and prompt are added and merged by a linear layer. Finally, another linear layer projects the fused feature to the original dimension. The structure and format of the CMT prompter remain consistent across different RGB plus X tracking tasks. By leveraging CMT prompter, we achieve the integration between RGB images and multimodal information with high efficiency through prompt tuning techniques. Although CMT prompter effectively complements auxiliary modalities as prompts, the prompt tracker lacks specialization for certain downstream tasks. For example, foundation tracker excels at localizing targets based on RGB images, while the lack of perception of linguistic features may result in suboptimal performance in RGB plus N tracking tasks. To enhance the adaptation to downstream tasks, we replace the vanilla transformer layers with tracking task perception transformer, TTP transformer, layers. Because the linear layer in transformer contains most of the knowledge of specific tasks, we only introduce few trainable parameters into each linear layer of transformer to bridge the RGB tracking and RGB plus X tracking. By leveraging CMT prompter and TTP transformer layer, prompt tracker inherits the strong localization ability from foundation tracker and achieves competitive performance on downstream RGB plus X tracking tasks after a quick fine-tuning on a small number of parameters. Given the minimal number of additional parameters, prompt tracker maintains a similar speed to foundation tracker. The whole training process of OneTracker consists of two stages: foundation tracker pre-training and prompt tracker fine-tuning. In the first pre-training stage, we pre-train our foundation tracker on a combination of several large-scale RGB tracking datasets, including LASOT, TrackingNet, and GOT10K. Because there is no mask annotations in tracking datasets, we leverage boxints to supervise the segmentation head of foundation tracker. In the second stage, we fine-tune our foundation tracker on RGB plus X downstream tracking datasets. We freeze the parameters of foundation tracker and only train the CMT prompters and adapters in TTP transformer layers. Our OneTracker outperforms other models and achieves state-of-the-art performance on 6 popular tracking tasks across 11 benchmarks. In summary, we propose a general framework, OneTracker, to unify several RGB tracking and RGB plus X tracking tasks. OneTracker involves pre-training a foundation tracker on RGB tracking datasets and adapting it to downstream RGB plus X tracking tasks using prompt tuning techniques. By leveraging the strengths of pre-training and parameter-efficient fine-tuning mechanisms, our framework achieves state-of-the-art results in various tracking scenarios.